Guys, I hope everybody's doing okay. We want to understand hypothesis testing today, and I want to learn this through an example. What I've got in front of me is a coffee machine. Okay, this looks really nice, but it is a coffee machine which dispenses some coffee, and it is calibrated to dispense a certain amount of coffee. Let's just say that amount is 80.23 milliliters per cup. Okay, so that is the amount of coffee that it dispenses per cup, and it is calibrated to dispense this much on average. So every time somebody takes a cup, there is some volume of coffee that could fit in the cup, and then somebody else gets another cup, and so on and so forth. Throughout the day, we look at all these different volumes, we calculate an average, turns out to be 80.23 milliliters. So that's an average amount of coffee this machine dispenses in a cup. Of course, if we can calculate average, we could always calculate standard deviation. Let's just say that standard deviation is 5 milliliters. Okay, so we've got a mean and we've got a standard dev for the volume this machine dispenses. Now, I'll get to why we do hypothesis testing, and I'm trying to build it to there. Look, if it dispenses 80.23 milliliters, I'm fine. This is what I calibrated this machine to. Okay, but and if it dispenses something like 80.24, I am fine with it. It's not a big problem. Even 80.25, that's okay. 80.19, I understand the machine could have some variability down to some decimal place, and that is okay. That is fine. That is part and parcel of the machine in itself. uh, but if it dispenses 100 cups, let's just say we're talking about 100 cups in a day. Okay, and if after 100 cups I figure out that the machine is dispensing 82 milliliters on average, then I have a problem, because not only is my caffeine intake spiked up, but other people using my coffee machine are probably getting a couple of milliliters extra too. So then this becomes a problem for me, where my coffee machine is behaving in a different way, and I should be concerned, I should be worried. But is this a and remember, we are calculating means, we are calculating sample means. So this is a sample mean for 100 cups. 80.19, 80.24 is another sample mean for another 100 cups. 80.25 is a sample mean for another 100 cups. So 82 that I came across is a sample mean for another 100 cups. So if I start getting values like 82, 84, I'm getting extra milliliters, and that should be a cause of concern for me. As long as there's small variation, such as in this case, 80.19, 0.24, 0.25, it should probably not surprise me. But this is what worries me when it goes to 82 or 84 or 90. That is something that bothers me. And I might be interested in knowing how reliable these values are, or should I be concerned? Or is this a one off value? Or is this a problem that I should be pretty much worried about? So, by calculating probabilities of such things happening, putting a number to 82 milliliters as an average coming out, putting a number on 80.25, 0.24, 0.19, putting a number, associating a probability with these numbers coming out, that is what helps me in determining whether I should be worried or everything's pretty much okay. So basically, hypothesis testing allows us to put probabilities associated with different cases, and based on those cases, we could determine whether or not we should be worried. Now, in my case, my null hypothesis, and the reason we call it the null hypothesis is because this is the base, or the usual, or the status quo. This is what usually happens, and we denote it by H naught. And we could say that for me, the null hypothesis, or the status quo, or what usually happens, is that this coffee machine dispenses 80.23 milliliters of coffee, and that's my null hypothesis. Uh, and my alternative hypothesis would be that this machine probably dispenses more than 80.23 milliliters of coffee. Now notice it could have been less than as well. It could have been not equals to also. So it depends on what I am interested in investigating. For this example, I'm interested in investigating if I'm taking in more caffeine than I need to from the calibrated value of 80.23. So I've gone ahead with the alternative hypothesis of greater than 80.23. So this is what I've set out to do. I've set out to see whether I get caffeine from this as greater than 80.23, but what I'm really answering, what what my computation is really going to help me determine is whether to accept or reject the usual case, the null hypothesis. This is what hypothesis testing does. It goes down to make a decision on whether or not you could run with the usual case, with the default case, or you can reject the usual case and there's some other phenomena that's going on, which is the alternative hypothesis. So that's what we're set out to do. Now, consider for this example that we have come across a sample mean value to be 82 milliliters, so 100 cups, and took an average for all of those 100 cups, and turned out to be the average value turned out to be 82 milliliters. The reason we do this now, the process that we're going to follow is to compute a test statistic. So this is what we do. This is how we put a number to, or a probability to our observations. We take a sample mean and we compute a test statistic. Now in our case we're going to use the z statistic, and this is how we go ahead with the computation. Notice this denominator is standard errors, so then this is scaled as standard errors. This is sample mean, subtracting the usual case, the mu, and then we get to compute a z value associated with it. So for us, this is going to be 82 minus 80.23 divided by the standard deviation of the population. For us, is 5 under root 100. And this should turn out to be some z value, which we can calculate. I think we can. Yes, let's calculate this right away on the fly. So it is 82 minus 80.23 divided by 5 over square root of 100. Let's fix the brackets here and here. This is what it looks like, and if we hit enter, we get 3.54. Okay, so we've got this test statistic z as 3.54. So we're 3.54 standard errors away on the normal curve. Now notice this is what the normal curve really looks like, and if we go ahead and look at in terms of the x values, the average value was 80.23, right? And on a z axis, this would equal to a 0. So that would be the mean. Okay, so this is going to take, I think, a minute to show up. Let's refresh. Okay, I think this is going to take a second, but I will continue to go ahead and interpret this value. So we've got 3.5. Oh, okay, it shows up right here. Okay, so we've got 3.54, which is 3.54 standard errors away from the mean value. Now, this is significant. This is important to us to be able to tell what does this really mean. So on a z on a z-axis where you're centered at 0, and now you've got a phenomena where 100 cups give an 82 sample mean value, which turned out to be 3.54. standard errors away, right? Now the problem is that what we're really interested in is this is calculating a probability, and that area of probability that bothers us is this one. It is right here. It is right here. And what does 3.54 really correspond to? We can just do a quick norm inverse. No, not the inverse. Click for the dist. 3.54 to that is 0.9997. But I will subtract this from 1 because the area is on the right hand side. 0.0002. Yes, so 0.0002. So this area is 0.0002. So we're looking at this area, which corresponds to basically 3.54 is the value, which has come from the test statistic related to an 82 sample mean. Now, why is this? What is this probability? We refer to this probability as the p-value. P-value is 0.0002. We refer to this as the p-value. What is this p-value indicating? What is this p-value telling us? That is of essence. That is the entire essence of hypothesis testing. The p-value is essentially telling us that this is the probability of, or the likelihood of 82 being a coincidence. Now, one more time. The probability, this very small probability, is a small likelihood that 82 was in fact a coincidence, right? It happened by chance. It's a very low probability, very less chance for this to happen, and that is intuitively also making sense, because notice under H naught, and this is an important observation. This is an important assumption, because the test is being performed using this assumption that you're performing this test under H naught, under the null hypothesis. This is what usually happens. Usually you get 80.23. And 80.23 is what you usually get. While this is the usual case, you observed an 82 sample mean, very high from the calibrated value. Notice the calibrated values are in 2 decimal places. This is altogether 82. This is 2 milliliters away. So under this assumption, under this basic base case, we have observed something very unusual, that the sample mean has turned out to be 82. The probability that this is a coincidence is so low. It's 0.0002. This probability is too small. And what that means is we cannot ignore such an important thing. We cannot ignore such an important observation. This is certainly not a coincidence, because the probability of it being a coincidence is so low. And therefore, what we must be doing is we must be alerted, we must think through, we must stop the machine. It's giving out extra 2 milliliters on every cup on average. So we must first of all reject or discard this null hypothesis. Okay, we must discard or reject the null hypothesis, because it is the alternative hypothesis that is dominating, which is what is happening. We observed a test again. We observed a test statistic, computed a test statistic based on our observation of a sample mean of 82 milliliters being dispensed by the coffee machine, and that corresponded to a p-value of 0.0002. And this told us that, look, this is not a coincidence. The probability is so small for it to be a coincidence that you got 82. It's so small that this is certainly not a coincidence. There's something wrong with the machine, and therefore you must reject the null hypothesis, the base case that it gives out 80 milliliters. So that is the essence of hypothesis testing. We accept or reject the base case, and that depends on what we observe and what the test statistic gives us out. and then it gives us a certain probability or a likelihood of that observation to be a coincidence. Turns out that is not a coincidence. There's very low probability this is a coincidence. Since a very low probability, it means it is definitely happening. And if this is the phenomenon that's taking place, the alternative hypothesis, the 82, this is something that's taking place, then we might as well just reject the null hypothesis. And we can safely say that this is not happening. The machine is not giving out 80.23 milliliters. This is not, the calibration has gone wrong, and we can safely reject the null hypothesis.